Now we shall be dealing with the concept that what would be the force on a current carrying conductor placed in an uniform magnetic field. First of all, observe that this is a current carrying conductor, which means some charges will be there in the form of electrons. And as we have seen in the Lorentz magnetic force, that if like a charge is drifting with the velocity placed in an uniform magnetic field. Now wherever we will use these concepts of B or E, that is the electric field, take it as uniform, right? So if there is electrons drifting in an uniform magnetic field, then obviously a force will be exerted on it, right? For these circumstances, let us see that how things actually happens. Say this one is the current conducting wire. Right? Obviously, this will have some cross-sectional area, and this cross-sectional area shall be uniform throughout its length. Right? And there is a magnetic field as such. Uniform magnetic field. This is the uniform magnetic field B. The direction is from this to this. Now, if we say that in this current carrying conductor, the current is passing in this direction, if this is the direction for the current or I, the direction for the drift of the electrons will just be opposite, as we know from the current and electricity, that if this is, say for example, a circuit diagram, and this is a resistor, this is a battery, plus and minus, then obviously the current shall flow from plus to minus. This is the direction for I. But the charge on the electron, it is negative, right? So in that scenario, the electrons will move just in the opposite direction, because they will flow from negative to the positive. So this will be the direction of the drift of the electrons. So if I is in this direction, the drift or the velocity vector for E will just be the reverse of this I, right? And if we are going to see a very small area of this, say for example we are taking a very small area up to this, right? Then the velocity vector of, say, this electrons present will be in this direction, right? Let us give us the term as V, the drift velocity for the electrons, just in the opposite direction of I. And let us check this length as dl, right? And the entire length for this one is, say, L. So now we can write that over here L is equals to the length of conductor and A is the cross-sectional area of this conductor. So this is the area A. Now we could tell that the volume actually for this GL part will be equal to, this is like a cylinder, right? So the volume will actually be equal to the area of the base, which is basically the cross-sectional area of this conductor, multiplied by the length. So this will be small v, right, a small volume. So we can write it as dV. For this V, we give it this sign so as to indicate that V is the volume over here. So dV now over this area will be equals to A multiplied by dl, right? It is equals to the small volume over this section is basically equals to this cross-sectional area multiplied by the length of this, right? Now, if over here it is being mentioned that N is equals to number of electrons per unit volume, then the actual number of electrons that is being present inside this area will be equals to N multiplied by the volume, right? So the actual number of electrons present in this part dl will be equal to the volume multiplied by this n, or n multiplied by this a dl. Now this gl, this is the length, obviously a length, which means the displacement has got a vector. We will take this gl, this vector, right, in the same direction along the direction of the current. So the direction of this gl will be likewise. So we can understand that the direction of this v, this drift velocity of this electron, is just opposite to that of dl, right? And we know that velocity is basically equals to the displacement divided by time. So we can write this v as equals to, right, dl divided by dt, and there will be a negative sign because this gl vector and this v vector are completely opposite, right? So, and this is the velocity with which it is drifting. Now, if we say that the actual number of electrons present in dl, then what is the actual total amount of charge which is being present in dl? Will simply be equal to the number of electrons present multiplied by the charge of each electron. Now what is the charge of each electron? It is simply equals to E as we denote. So amount of charge present in dl is equals to n multiplied by A multiplied by dl multiplied by the charge, that is electron E, right? Now, as we know that this is the amount of charge, right? Now, the amount of this charge in electron, either it is positive or negative. Yes, this is simply negative. So, this will be a negative sign in front of NaDLE, right? Now, we have got that what is the total amount of charge present in dl, what is the drift velocity, what is this uniform magnetic field. Now, as we know from the Lorentz magnetic force, we can write as let us simply first write this as like this, the magnitude. This will be equals to, simply not the magnitude first of all, let us take Fm, the Lorentz magnetic force as we denoted, will be equals to the amount of charge. This is the amount of charge. It will be equals to minus NaDLE multiplied by the cross product of this drift velocity with this magnetic field, right? So it will be V cross product with B, right? Now, will this be the total, like say the Lorentz magnetic force on this entire conducting wire? Obviously not, because we have taken the case that this is only for dl. So this amount of force will just be a small amount of force that will be experienced over dl only. So we need to say that this will be like this, right? So we can replace now this V as equals to minus of dl divided by dt. If we do so, see, this is a negative sign and this is a negative sign, it will cancel out and it will become positive. So it will be n multiplied by A multiplied by dl multiplied by E divided by dt, because we have taken this dt outside and this dl, this is a vector and this is B, right? Now look over here, what is basically NaDLE? This is simply the charge, the small amount of charge NaE present in dl. This is the small amount of charge. So we can write this small amount of charge as over this expression as dq, the small amount of charge, the total charge present in dl. So we can write the next step as this is dq divided by dt dl cross product with this uniform magnetic field. Now remember, from current in electricity, what basically is the amount of charge passing per unit time, that is dq by dt. It is simply equals to this I, right? The amount of current. So we can write it as I multiplied by the dl vector cross product with B. Now see, this is the small amount of Lorentz magnetic force that we are dealing with over this area of dl. Now if we want to find out the total amount of this Lorentz magnetic force over this entire current carrying conductor, we need to integrate it for the entire length. What is the entire length? L, right? So we can write that the total Lorentz magnetic force which is applicable over here will be equals to I simply multiplied by L multiplied by B. Why? Because this was for DL. Now we have integrated the entire thing. Because, for example, if we wanted to find out this Lorentz magnetic force, we needed to integrate it over L, right? So we have now integrated it, this DL over the entire length. So this comes out to be like this. And now if we wish to find out the magnitude of this Lorentz magnetic force over this entire current carrying conducting wire or conductor, it will simply be equals to B I L sine theta. Now what is theta over here? Yeah, simple. See over here, this is V and this is B. We are actually interested not in V and B right now. We have started off with V and B but ended up with L cross B. So we need to understand the angle difference between this L and B, right? So this angle difference between this, or the angle which is being made between this DL, this one, and the B vector will simply be equals to theta, right? Now we can take up the cases that say, for example, case 1, where it is given that the theta is equals to 0. What does it mean? It means that this DL vector is parallel and in same direction with B, right? So we can write this L and B are parallel and in same direction. At that point of time, see, this sine theta will be sine 0. That means it will be simply equals to 0. Sine of 0 is equals to 0. So the entire term will become 0, which means that now if this L and B, they are parallel and they are in the same direction, no Lorentz magnetic force shall be exerted on this conductor. So we can write this F M is equals to 0. Now again, if we make that this theta now is equals to say pi or 180 degree, which means at that time the DL will be on this side, the I will be flowing in this side and B will be on this side, which means that the sine of pi over here and the value of sine of pi is again 0, right? So again the Fm will come out to be 0. So we can say that either if L and B are simply parallel and in same direction or opposite direction, in both the scenarios the Lorentz magnetic force which is exerted over the entire current carrying conductor will simply be equals to 0. Now if we take the second case as say, for example, we are taking the case when theta is equals to pi by 2, which means that L and B are simply perpendicular to each other, which implies that L is perpendicular to B, right? They are mutually perpendicular. See over here, it will be sine of pi by 2. That means equals to 1. So the Fm that will be exerted will be the maximum is equals to BIL. So we can write that the magnitude of Fm exerted will be equals to BIL. This is the maximum and this one found out is the minimum. Now wait, we have found out on the entire note that what will be like the magnitude of this Lorentz force as being a vector quantity. What will be the direction? If say for example, if L and this B, we take this scenario, L and B are mutually perpendicular to each other, take out your left hand, stretch this thumb, index finger and middle finger only in such a way that they are mutually perpendicular to each other. See, this is perpendicular to this as well as this is perpendicular to this. Again, this is also perpendicular to this. Okay, stretch it out in such a way. In such a way that your index finger, it points the B. So, let us check that on the direction, the index finger, you stretch out as such, it shows the direction of B. And your middle finger, it shows the direction of the current or I, right? Then in that scenario, the thumb of your left hand will give you the direction of the Lorentz magnetic force. This scenario is famously, this postulation is famously known as Fleming's left hand rule. Why? Because whatever you are doing over here, say the index finger, middle finger or the thumb, they are of your left hand, right? So over here, stretch it likewise. See, the B, right? If they are mutually perpendicular, this I will point this index finger towards B, right? This I, this middle finger, this one towards I will point it out. When in the case 2, that they are mutually perpendicular. Take it that over here now I is mutually perpendicular to B. So if I point the index finger towards B, obviously I will get my middle finger in the direction of this flowing of I. Then see, the pointing of the thumb will say me the direction of the Lorentz magnetic force. See, it is coming outside from this white board, or it is going towards the reader, right? So for example, if you are only given the direction of the force and the direction of this current, again we could be able to find out the direction of B with the help of this Fleming's left hand rule. So here we have found out that what would be the magnitude of this Lorentz magnetic force that is enacted on a current carrying conductor when it is placed in a uniform magnetic field of B. And also after that we have understood that how to find the direction, that we need to first of all take our left hand, stretch the index finger, this one, as such that it will point towards the direction of the magnetic field. Then stretch your like this middle finger as such that it will point towards the direction of the current, and again stretch your thumb. This thumb will now show you the direction of the Lorentz magnetic force, but be very cautious. All these three fingers need to be mutually perpendicular to each other. Right? Thank you.